now I want to talk about how do we get the age of Earth. Your book says the age of Earth is 4.57 billion years old. We get that looking at meteorites, right? Because remember, the early planet was so hot, there was so much heat flow that we couldn't form rocks. In fact, the first rocks, some of the oldest rocks we can date today are about 4 billion years old. There's some evidence now that there's some rocks about 4.3 billion years old. Nonetheless, how do we get the age of Earth if we don't have a closed system? Well, what was the only thing that was closed back then? Were the heavy atom objects that were moving around the solar system, crashing into each other, making larger heavy atom objects, and those are called the planetesimals, right? So these are heavy atom objects in the early solar system, right? The solar nebula. So when we look at these meteorites, because they're going to have the closed system, and we can use them to take us back to the beginning of our solar nebulas of our solar system and planet Earth, we find that there are two general types of meteorites. There's one called a trollite, and trollite are mostly these iron meteorites. And what they represent the cores of these planetesimals, right? And eventually they crash into each other, and if they explode, then these bits of meteorites are floating around the solar system. And they're still around here. And I have one right here. You can see this is a nice little iron nickel meteorite, and you can see it kind of looks like an old nickel there. This meteorite is called an iron meteorite or a trollite, right? Then the next meteorite, I'll leave the trollite there, is one called the chondrite, right? So chondrites are going to be more like rocky material, right? They represent differentiated parts of the planet, like the lower mantle or middle mantle, or maybe even some of the crustal areas. And I do have an interesting one right here. You can see that here's an iron meteorite, but this one actually has some minerals in it. And those minerals are olivine crystals. There's a pretty large olivine crystal in that one there. So that represents something where there's been some differentiation, where we're actually forming olivine crystals there. And then as we go farther along, we see some other chondrites here. Now, you can see some metal in that, but not as much. It seems to be more speckled. There are other minerals in here, right? So there's some other minerals, maybe small olivines in there, some magnetites in there, a variety of different minerals in that one. So this one seems to be, so if that's going to be our core, our iron meteorite, this is going to be part of our lower mantle. This is going to be somewhere in the mantle. And then finally, as we go farther along, here we have one that looks like a rock, right? So here, this one looks like a rock. It's been cut with a saw, so that's why I have them in these nice little shapes here. And so this sample here would be more toward the upper parts of the mantle, or maybe even some crustal areas of these planetesimals, right? So in other words, the meteorites were solid objects when the solar system first formed, right? So we have these heavy atom objects, right? And then they crash into each other and explode, and little asteroids and meteorites are floating around. And every once in a while, they hit our planet, and we collect them, and we analyze them. Now, so the significance of these is, or the key, is this next part here. The trollite has no uranium. So trollite has no uranium, which means it's not going to grow any radiogenic lead. So the lead that we measure from these trollites, from these iron meteorites, that lead is important because it's going to be what we call primordial lead. And that primordial lead is the initial value of lead in the universe, right? So that gives us a foundation, a starting point for lead in the solar system. Anything that deviates from that would have grown through the decay of uranium, right? So, because remember, there's going to be two of those isotopes of uranium that decay to lead. And so the chondrites, which are these rocky ones up over here, these chondrites vary in the uranium concentration. So usually what we say is that this palisite here would probably have the lowest amount of uranium, and whereas this rocky chondrite here would probably have the highest amount of uranium. But because they vary in their uranium concentration, they're gonna have different amounts of radiogenic lead. But the key thing is they're going to grow radiogenic lead. So I call this next part the lead-lead evolution curve, right? Because remember, there's uranium-235, and this uranium-235 decays to grow lead-207, right? Lead-207, whereas uranium-238 decays and grows to a stable daughter product of lead-206. So lead-206 and lead-207 come from uranium. And so the way we look at this is we want to figure out where these trollites plot, because remember, trollites have very little uranium. They're going to plot somewhere down in here, right? So these are going to be the iron meteorites, the trollites, going to plot down in there. And they pretty much all plot right in this value there. But these chondrites, because they vary in their amounts of lead, they're going to have higher 206 and higher 207. So they're going to plot out in a line like this. So the ones that have more uranium will have more 206 and more 207. The ones that have less uranium, like this one here, will have a little bit less 206 and a little bit less 207. Obviously, the iron meteorites can have the smallest 206 and smallest 207. So when you plot these, they essentially make a straight line. And so we'll line these up here. So we'll have a value like that. And what's interesting is because we're using isotopes that have grown from the decay of uranium, so they're radiogenic, this curve, there's, you probably know the equation y equals mx plus b. Well, this m is the slope of the line, and that slope of the line has age significance. So if you calculate the slope of the line, it's 4.55 GA. 4.55 GA. So that's how we get the age of the solar system, by looking at the meteorites. Now, another thing that we did is one place on Earth, we have all these galenas. And galena is a very metallic mineral, has metallic luster. It's very heavy because it's composed essentially entirely of lead. You can see it has a nice cubic cleavage here, right? And so this is a lead sulfide. And if you analyze all the galenas on Earth, these young galenas, the galenas fall right in here. And then also another thing, if you could sample a well-mixed sample of Earth, if you can go somewhere on planet Earth and find out where you're sampling rocks over a huge area, you can get an entire Earth representative. Because remember, Earth is another rocky object in the solar system. And we go to a river mouse. In fact, the Amazon or the Orinoco rivers in South America, because they sample a huge craton, a huge part of northern South America, and they funnel it down to the delta. So if you sample that sediment, we find that sediment also falls right here. So this is young Earth, or well, it's a young Earth sediment. So that also falls in that line. So this just tells us that Earth also falls in this line. So Earth also has the same age. And if we look at the PowerPoint here, so we got this slope of the line based on isotopic dating of meteorites and asteroids, which are planetary fragments. And meteorites and planetary fragments formed at the same time as our solar system. So the age of Earth is the same age as Mars, same age as Jupiter, same age as Mercury, same age as Venus, same age. They're all, and when we do this, we get an age of about 4.55 billion years. So here's another look at that graph. We got the 207, 204, 206, 204. We normalize the isotopes to 204 because 204 is stable. It doesn't have a radioactive parent. So whatever 204 the solar system started with, we've always had that 204. But you can see the iron trollites plot down here, very low values of 207 and 206. But then the chondrites plot at a varying concentration. But see, they plot on the same line. And note that the modern sediments and young galenas also fall in this line. So that's how we get the age of the Earth. And this line is called the Geochron. That line is called the Geochron.